We're going to take a look at a classic physics problem, a person standing on a scale in an elevator. And as this elevator accelerates up and down, we want to look and see if we can figure out what the scale reads. This is a classic problem you'll find at the end of the chapter in every physics textbook. But it's a very simple problem. And yes, I guarantee our dynamics problems will get much more complicated as we move through the quarter. But the procedure we would take when we set up the problem and work through it is the same. So I'll formally go through that and kind of outline how I set up and solve a dynamics problem. Of course, the first thing you need to do is identify the lens. Are you going to use dynamics? Are you going to use kinematics? Are you going to use work and energy? What lens are you going to use to solve the problem? So I'm assuming you've done that and you've decided to use dynamics. Now let's go through and outline the procedure for solving a dynamics problem. In this case, why would we pick dynamics? Well, there are forces acting on our person. The person is standing on a scale, which means there's some kind of interaction there, a normal force pushing up, their weight pushing down. Oh, their weight is pushing down. That means the force of gravity is acting on them. So we know there are some forces acting on them, and we know there's acceleration. We're told the elevator is accelerating upward at 2 meters per second squared. And if we're given forces and acceleration, we kind of think dynamics, F equals ma. If they were asking for a velocity, well, there is no velocity in F equals ma equation, so we'd pick maybe energy or kinematics. We'd pick a different approach. But in this case, we're going to use dynamics. And the first thing I like to do to help me wrap my head around what's going on is draw a free body diagram. So here's my person. At this stage in our mechanics class, every object just looks like a point object, because if you give an object dimension, then it could rotate on you, and we can't deal with that yet. But don't worry, we will be able to deal with it by the end of the quarter. But right now, everything kind of looks like a point object, so this is not so important as to where the force is acting on the person. But by the end of the quarter, we want to draw a free body diagram that represents our object and where the force acts on the object, because that is important for rotation. So I'll sort of try to do that. My force of gravity is going to act on the center of mass of my person, so force of gravity. And acting on my feet is the normal force. And we always put the tail of the vector on our object and draw the vector out from there. So we've got the force of gravity and we've got the normal force. If you can, you want the length of your vector to be proportional to the magnitude of that force it represents. Did I draw these correctly? I did not, because I know the acceleration is upward. That means there has to be more force in the upward direction than down. And I drew my force of gravity bigger than my normal force. So I'm going to correct that now. Sometimes you can do that. Sometimes you can't. Sometimes you don't know. So we know in this case the normal force has got to be a little bit longer, a little bit bigger in magnitude than the force of gravity. If you don't know, that's okay. Just make sure you indicate there's a force there and what direction it points, and you can solve for the magnitude later. We're going to use this equation to solve for our unknowns. Sum of the forces equals mass times acceleration. But before we can do that, we have to define a positive direction because these are vector quantities. Now we can set up our equation and plug in our values. Okay, so let's go through it for this problem. I've got my free body diagram. I'm going to use the equation sum of the forces equals ma, and I'm going to pick up as my positive direction. So I'm adding the forces just in this vertical direction. I could write this as, we could call this our positive y direction, and I could say sum of the forces in the y direction is equal to my mass times the acceleration in the y direction, and I'm calling up the positive y direction. So I want to be clear as to what my positive direction is. Now when I look at my free body diagram, this is very helpful. I know that I have two forces in the y direction. One is pointing in the positive y direction, one is pointing in the negative y direction. So I take into account my signs now. So I've got two forces here. So I'm adding up all my forces in the y direction. There's two of them. So I'll have two terms here, a normal force and a force of gravity. And normal force is in the positive direction, and the force of gravity is in the negative direction. I don't need to put a plus sign there. I know it's positive if I don't have a minus sign, right? Those will add up to be the mass times the acceleration. Now I'm ready to substitute and solve. Let's make our person be 50 kilograms. Our acceleration is 2 meters per second squared in the upward direction. And we want to know what the scale reads. And the scale is telling us the normal force. That's the interaction between our feet and the scale. That's the normal force. You might notice here, because I've got the minus sign here for the direction of the force of gravity, when you go substitute numbers in, this must be positive now. You could think of this as having absolute value signs around it. That has to be a positive number. That has to be the magnitude of the vector that represents the force of gravity. These are magnitudes now. Why are they magnitudes in this equation? Because I have already accounted for the direction with that minus sign. So I've got my normal force. What is the force of gravity? That's just equal to the mass times the acceleration of gravity, g. And little g is always positive. And if we're using the metric system, it's 9.8 meters per second squared. Always positive when you see a little g. They assume you will account for the direction elsewhere, like we are here, if it happens to point in the negative direction. But g is always positive. And this is going to be mass times acceleration. So our normal force is going to be ma plus mg. And our mass is 50 kilograms. And the acceleration is in the positive direction. So I'm just going to write here positive 2 meters per second squared. I know I don't need that plus sign, but just to make sure you understand, we're putting in the acceleration and we know it's in the positive direction. And we're adding to that 50 kilograms times g, and I'm just going to use 10 meters per second squared for g, approximately 10. I know it's 9.8. If I had a calculator handy, I'd use 9.8, but I don't. So I'm just going to use 10 so I can do this in my head. And what do I get? I get 100 kilogram meters per second squared is a newton. And I'm adding to that 500 newtons. The normal force acting on the person in the elevator is 600 newtons. And it makes some sense. 500 newtons is our weight. If the elevator wasn't moving, the scale would be pushing up with a force of 500 newtons just to hold us up, just to hold up our weight. And the extra 100 newtons, this extra amount, this extra 100 newtons, is what is providing the acceleration of 2 meters per second squared in the upward direction. So you could almost split up the normal force and say part of it is just holding up your weight, and this extra part we're getting is providing the acceleration. What would happen if instead of the acceleration being up, the acceleration was down? So our elevator is still moving up, but now it's slowing down because we're getting close to our floor where we have to get off. So what would our normal force be in that case? Well, we've got the same free body diagram, right? Gravity and a normal force. But this time we know the normal force has to be less than the force of gravity because we have to be left with a net force that's in the same direction as our acceleration. Let's make it 2 meters per second squared in the downward direction. So I've drawn my free body diagram. I'm going to say the sum of the forces in the y direction is m times the acceleration in the y direction, and my positive direction is up. So I have 2 forces in the y direction. The normal force is in the positive direction. In the negative direction, I have the force of gravity. That has to add up to be m times a. Force of gravity is just mg. Now I can plug in. I've got 50 kilograms for my mass. For my acceleration, I have 2 meters per second squared in the negative direction. Don't forget your minus sign. I've got 50 kilograms for the mass. And g, I'm going to use approximately 10 meters per second squared. And it's positive. This is a positive number, 10, not negative, because I've already accounted for the sign over here. The negative sign showed up there. And the normal force you feel when you're in an elevator, we call that, we have a special name for that. We call it the apparent weight. Your weight never changes. The force of gravity between you and the earth never changes. Your weight is the force of gravity, is mg. That never changes as long as you don't leave the surface of the earth. As long as you're close to the surface of the earth, the force between you and the earth, that gravitational attraction, is always the same. What changes is the normal force. So when the elevator is accelerating upward, what do you feel? When you're standing in that elevator, you feel heavier because it's pushing on you to try to get you to accelerate, and the inertia of your body resists that, and you feel heavier at that time. When the elevator is moving at constant speed or when it's at rest, you feel your normal weight. You can't tell if it's at rest or if it's moving at constant speed. You feel the same either way. And when the elevator slows down as it's moving up, and it slows down because you're getting close to your exit, you feel lighter. Your body's inertia wants to keep going, but the elevator's slowing down underneath you, and the interaction between your feet and the floor is less. It's like you're lighter. You don't feel as big a force between your feet and the floor. And that's your apparent weight. That's the normal force acting on you. So, of course, for any problem, you want to identify the lens first. Once you do that, once you decide to take on dynamics, because you know there's forces and accelerations involved, and you know F equals ma, so you decide to use that approach to solve the problem, then you would follow this procedure. You would draw a free body diagram. Use the equation F equals ma. This is a vector equation. In order to use it, you have to define positive directions. Then you substitute and solve. This same procedure for solving even complex dynamics problems.